Hello everybody, so today I am, there we go, I was going to say my screen disappeared. Today we were talking about trig identities and solving trig equations. So yesterday I basically went through the bulk of chapter 4. Today I'm basically going through the bulk of chapter 5, distilling the most important things that you need to know to be successful for this week and going forward. So I'm going to just start by going through all the identities just so you have them all in one place. So we have the fundamental trig identities, sine, cosine, tangent, and then it's showing the relationship to reciprocals. So this was also covered in yesterday's session. And then quotient identities, so tangent and cotangent. Tangent is the same as sine over cosine, and cotangent is then the reciprocal, cosine over sine. And then we've got these Pythagorean identities. So these come from the Pythagorean theorem. When you have a unit circle, x is your cosine, y is your sine. So x squared plus y squared equals 1. So cosine squared plus sine squared equals 1, or sine squared plus cosine squared equals 1. And then you can convert those to tangent, cotangent by using the quotient identities and then doing some algebra. Co-function identities, these are actually basically the same as the shifts that we saw, the complements yesterday. Those were in reference to 90 degrees. 90 degrees is the same pi over 2. So these are just the same thing, just written differently. Even odd identities. So this shows a relationship to a negative angle and what it's equal to if you don't want to deal with a negative angle, and you can flip it. So if you have the sine of, let's see, we had an example. The sine of negative 2/3 over pi would be the negative sine of 2/3 over pi. And so, let's see, do I have a unit circle around here? Yeah, I have one on here. So 2/3 over pi is what I was saying. 2/3 pi, the sine is square root of 3 over 2. Yesterday when we had it, so the negative, that would be negative square root of 3 over 2, which corresponds with our answer from yesterday's example. That was the first example from yesterday that you can use these even odd identities. So let me just write that down. So yesterday, we were finding the sine of negative 2 pi over 3, which is equal to negative sine of 2 pi over 3, which is negative square root of 3 over 2. So we did not use the even odd identity to find our answer. We took a look at the unit circle and then drew our right triangle based off of where the angle was, but you get the same answer. Okay, now when you're solving trig identities, you need to worry about the period. So the period is the length of one cycle of the function before it starts repeating. This is usually referred to as graphically, where does it, if you graphed these, where does the shape start to repeat, basically. So the period for most of our trig functions is 2 pi. 2 pi is 360 degrees. What that means is that I am looking for, let's say I'm starting at 0, my cosine here is 1, which is the x value. I'm not going to get a cosine of 1 until I go all the way around a circle and I come back to where I started, which is 360 degrees or 2 pi. Tangent, on the other hand, is pi. So that means whatever the tangent is here, where I have a circle, is the same value of tangent here. So you would have the same value for tangent. So tangent is not listed on this graph or on this unit circle, but you would get the same value. Now, that's a bad starting point because that's undefined. But let's start here. So tangent is sine over cosine. So it would be the 1/2 over square root of 3 over 2. So it's 1 over square root of 3. If you travel pi, then you get the same values but negative signs. The negatives would cancel. You would get the same value for tangent, 180 degrees or pi degrees. So that's what the period is. And that's going to be very important when we're solving, because when you're solving, that means that there are infinite solutions, because this is a cycle. It just keeps going in circles. And so there are infinite solutions, and you need to either pay attention to whether they give you a domain, or you have to indicate their infinite solutions by having a variable n to show the pattern, where n just starts counting from 1, 2, 3, and so on. This will make much more sense as you see it. And on all of these problems, I have a unit circle added because I always have to look at the unit circle to understand how all this is working. And we're also going to have to remember the period here. So keep that handy. Just remember everything is 2 pi except for tangent and cotangent. Okay, so we need to solve tangent of x plus the square root of 3 equals 0. So first, in order to solve these, you want to get tangent by itself. So I'm going to start by subtracting the square root of 3 on both sides. So we get the tangent of x equals negative square root of 3. Now what this is saying, we are looking for x. We are looking for the angle. The tangent of what angle will give us negative square root of 3. That is essentially what this is asking. So there are two ways to do this. There's one way to do it, which is with your calculator. And if you need to do this, you need to make sure you're in the correct mode. So on the calculator, we're going to use what is called arctangent, which is basically taking the inverse, which is the different, is not the same as the reciprocal. And this is indicated by writing arctan. So it'd be, we're taking the arctangent of tangent of x. We're doing this on both sides. So arctan of the right side, negative square root of 3. So arctan and tangent, those are inverses, so they cancel out, and all you're left with is x. And then you get arctan of negative square root of 3. Now, calculators don't generally write as arctan. The calculator will write it as tan to the negative 1. This is not 1 over tangent. This is the inverse tangent. It's much like function notation, because tangent is a function. So it's function notation where the negative 1 indicates that it's an inverse. So your answer depends on whether your calculator is in radian mode or degree mode. We generally do everything in radian mode. So just default to radian mode. So you want to make sure that you're in radian mode. My calculator is in radian mode. And then above my tangent button, there's a second button to get the arctan. And then I can type in negative square root of 3. And it's going to give you a decimal answer, which is gross. I got negative 1.0471975551. It's a gross number. If you have a graphing calculator, it will give it to you exactly. So I have both. So I just did that on my basic calculator, the TI-30X. If I do the same thing on my graphing calculator, which I also have in radians, it tells me that this is equal to negative pi over 3. So if you have access to a graphing calculator, I recommend it, because then you're not dealing with decimals. So now we have an idea, we know what the angle is. So negative pi over 3 means I'm going pi over 3 in the negative direction. But let's think about this. We can use our even odd rules. So I have a negative angle. So you can see that a negative angle for tangent is equal to the negative of the tangent of that value. So just keep that in mind. Let me go through my example here. So this means basically that, oops, I'm on the wrong slide. That the tangent of negative pi over 3 is the same as the, oh, I just forgot. What did I say it was? The negative tangent of pi over 3. Those are the same values. So pi over 3, this is going to give us the same value as the negative tangent there. So I'm going to just write this in another color. So the tangent of negative pi over 3 is equal to negative tangent of pi over 3. So you can just see that relationship there. So I'm going to just draw that in green just so you can see that those are basically, if you knew what the tangent is pi over 3, then you just switch the sign. Anyway, that is just a side note showing how the even or odd rules are. What we really need to know is this period business. So we know what x is, but tangent has a period of pi. So that means, I'm going to do this in purple, that we need to add a pi to our function to get another value of tangent. And then we multiply that by n, because the period, each time you add pi, you're going to get the same value. So we have to multiply, add pi, just kind of continually. Now, generally, when we write our answers, negative pi over 3, we don't like to write this with negative angles. We prefer to write it with positive angles. So when you add pi to pi over 3, you get 2 pi over 3. So we really want to write this as x equals 2 pi over 3 plus pi times n. And then that will make sure that we get each value in our unit circle that has that same value that is going to make that equation true. Now I'm going to just do a little side note here for those who may not have a graphing calculator and can only get decimal values, which is really difficult to translate. How do you convert that decimal value and figure out what it is as a pi? You know, that's very difficult. So I'm going to we can do this with the unit circle, or with the right triangle here. So we got negative pi over 3. Pi over 3 is 60 degrees. So let's say that's 60 degrees. And notice this, we can do this using our even odd rule. So negative tangent of 60 degrees. Basically, we're looking at what that is equal to. And since our tangent of negative 60 degrees is negative pi over 3, so this is going to be not negative pi over 3, negative square root of 3. The negative tangent of that is square root of 3. So keep in mind our 30, 60, 90 triangle from yesterday, where the hypotenuse is 1. And then across from 60, we have square root of 3 over 2. And across from 30, we have 1/2. Now this triangle is not drawn to scale. If I multiply everything by 2, then this comes to 2, 1, and square root of 3. So if you did not know what the angle was, did not know it was 60 degrees, you could then say, okay, at what angle is the opposite over adjacent equal to square root of 3. And so that would be the 60-degree angle. So you can draw your right triangle trig, figure out the correct relationship here, tangent, and then figure out what angle goes with that. So there's a way to do it that way. It's a little harder and involves more thinking, but you can figure out this stuff without having a graphing calculator. Okay, so now I've got example 2 here. So we need to solve 3 sine of x plus 1 equals sine of x. So we want to get the sine of x by itself. We're going to isolate that. So I'm going to subtract 3 times the sine of x from both sides. It leaves me 1 equals negative 2 sine of x. Now we're going to divide everything by negative 2. So you get negative 1/2 equals the sine of x. So now we're looking for x. We're looking for the angle. And sine is the same thing as y on our unit circle. So where is our y value? Negative 1/2. So that gives us at 11 pi over 6. And then we have another one at 7 pi over 6. So we can use the unit circle to figure out that our angle, our x, must be 7 pi over 6 and 11 pi over 6. Those are the 2 places where the sine value is negative 1/2. So I can use the unit circle to figure out what x is without having to use my calculator here because it's one of the standard angles. If it's tangent, I usually use the calculator because it's a little harder to figure out tangent on the unit circle because the unit circle only shows you sine and cosine. If you make your own unit circle, you could also write down all the tangent values on your unit circle, and that could help you out a lot. I don't do that. I just refer to the unit circle with only the ordered pairs, the sine and the cosine stuff. So that's why I use my calculator when it comes to tangent. So we've got 2 values here for x. And now we have to consider the fact of the period. The period is 2 pi. So if I'm at 7 pi over 6, I'm going 360 degrees before I'm hitting there again. So I need to add 2 pi, and I have to multiply that by n. 11 pi over 6, I'm going 360 degrees. I'm going around the circle, and I'm coming back at where I am. So that's another one I have to add, 2 pi n. So I have 2 values for x, 2 answers here, because these are 2 separate locations, and if I add 2 pi, I'm not going to hit the other one. So I need to have a separate equation for both of these points, because adding 2 pi is never going to hit the other point. That's part of the answer. So that's how we write our answers for this one. Okay, now here's another one with sine. So to solve this, you want to get your sine by itself. So I like to deal with positive parts, positive values. So I'm going to add 4 sine of x to both sides, sine squared x plus, can't talk today. This is going to give me 2 equals 4 sine squared x. So sine squared x is the same as sine of x squared. It's just a different notation. So that means we can take the square root of this. But first I need to get it by itself. So I'm going to divide everything by 4. So I get 1/2 equals sine squared x. And now I need to take the square root. And when you take the square root, you get plus or minus. So we're going to get 2 answers here. So I have plus or minus, and the square root of 1 is 1. So I get 1 over the square root of 2 as my sine of x. And we need to rationalize that. That is equal to plus or minus square root of 2 over 2. And square root of 2 over 2, that is a 45-degree angle, which is pi over 4. So we know that our x is pi over 4. Now we need to figure out where are all the places that we get square root of 2 over 2. And because it's plus or minus, we have multiple. We have to consider the y value to be positive and the y value to be negative. So sine is the y value. So I've got one at pi over 4 and at 3 pi over 4. And I can also have negative y's, so that is at 5 pi over 4 and 7 pi over 4. So I've got 4 different possible values here. So I could write, because the period of sine is 2 pi, I can write 4 separate equations for sine, each of them adding 2 pi. But there's actually a relationship here that can allow us to minimize this. Because if you notice, if I go from pi over 4, I can get to 5 pi over 4 by adding pi. And then if I add pi again, I get to pi over 4. So I can actually hit 2 of the answers with one equation by adding pi instead of 2 pi. And I could do the same thing with the other one. I can take an equation for 3 pi over 4, add pi, and then I hit 7 pi over 4. Add pi again, I get back to 3 pi over 4. So I can narrow this down to 2 equations. But if you notice, we can narrow this down even further by adding pi over 2 instead. Because if I add pi over 2, which is 2 pi over 4, that gets me to 3 pi over 4. Add 2 pi over 4, I get to 5 pi over 4. There's the distance between all 4 of these points is constant, so I can create one equation by adding that distance. So I can write my answer as, oops, make sure I'm in pen mode, not highlighter mode. X equals pi over 4 plus pi over 2n, because the difference between each of these is pi over 2. There's a pattern. So as long as your period can be divided evenly and you hit all of the points, then you can create one equation. So you don't have to always add 2 pi and have 4 separate equations. We can actually capture all of our possible answers with one equation by thinking about what is the difference between each of these. What is the constant difference? It's sort of like writing a linear equation in a way. Okay, now this one's trickier. The first one's a pretty straightforward tangent, sine. I haven't done a cosine one yet. This one has secant and cosecant. So we don't really like to work with cosecants and secants. And so your goal is to try to convert it into something with sines and cosines if possible. And so if you're looking at this, your first instinct might be to divide both sides by cosecant of x. We do not want to do that, because if you do that, you are ignoring a solution by dividing out a solution. And you have to make sure that you can only do that if the thing doesn't equal 0. If your cosecant of x can equal 0, then you're dividing by 0, which is impossible. So just generally never divide anything, never ever divide both sides by x to solve. We don't do that in normal equations. If there's x on both sides, we never try to do that. So don't do that. Instead, try to put everything on one side so we can factor out the cosecant of x. So I'm going to subtract the 2 cosecant of x from both sides. So I have secant of x times cosecant of x minus 2 cosecant of x equals 0. Now, I only know what to do here because I've done lots of these. Solving these kind of things, there's a lot of little tricks to try to see which ones work. Some don't. It's a lot of trial and error. So if this is not intuitive to you, don't worry. This is just because I've done a lot of these. So I'm going to factor out cosecant of x, which leaves me with secant of x minus 2 equal to 0. So we can use the zero factor property. It's the same thing that you use when you have a quadratic. You set each factor equal to 0. We can do that here. So I have cosecant of x, cosecant of x equals 0, which I notice I said that we can't divide by that if it's going to equal to 0, so this would have caused a problem. And then secant x minus 2 equals 0. And so we're going to solve both of these. And so solving cosecant is not easy to me. That is 1 over sine. So I'm going to convert this to 1 over sine of x equals 0. Now, if I multiply both sides by sine of x to kind of get rid of the fraction, we would end up with 0 times sine of x. You get 1 equals 0. So what that means is that this doesn't give us any solution. There is no solution from this part, because 1 equals 0 just doesn't mean anything. So let's solve the secant squared part, or secant part. So I'm going to add 2 to both sides to get secant of x equals 2. Now secant is 1 over cosine, so I'm going to convert this to 1 over cosine of x equals 2. And I can take the reciprocal of both sides to get cosine of x, or I can multiply both sides by cosine x and then divide everything by 2. But that's the same as taking the reciprocal. So the cosine of x is equal to 1 over 2. So now I'm looking at all the angles where my cosine, which is the x value, is equal to 1/2. So I'm looking for x values that are 1/2. So I have one at pi over 3 and at 5 pi over 3. So now we need to add the period, and we have 2 separate equations, and your question might be, well, is it possible to distill this into 1? And it's not, because the difference between these is not constant. The difference in one direction is this really long angle. The difference in the other angle is this very short angle. So it has to form a pattern of be divided evenly here. But because it's not evenly divided in half, quarters, or some sort of thing like that, we need to have 2 separate equations, because there's no way that I can go from 5 pi over 3 to pi over 3 and then use that same distance to get back to 5 pi over 3. The distance there is not the same. So I need 2 equations here. So my first one, x equals pi over 3, and cosine has a period of 2 pi, so that's plus 2 pi n. And then my second one is 5 pi over 3, so x equals 5 pi over 3 plus 2 pi n. So we get 2 solutions here. We have to have 2 separate equations for them. All right, so now this is find all the solutions to cosine x plus sine x tangent x equals 2 in the interval from 0 to 2 pi. They're giving us an interval, which means we don't have to worry about the adding pi times n, 2 pi times n, any of that stuff. We can just find the ones that are on the unit circle, because the unit circle is from 0 to 2 pi. So we've got a cosine, sine, and tangent, and something equal to 2. So if I see things with sine, cosine, and tangent, I like to use the relationship or the identity that tangent is sine over cosine. So I will rewrite tangent as sine over the cosine and then see where that takes me. So I have cosine x plus sine of x times sine of x over cosine x equals 2. So if I simplify this, I get cosine x plus sine squared x over cosine x equals 2. So now we have two potential things we can do here. We could multiply both sides by the cosine of x to get rid of the fraction and see what happens there, or we can try to get a common denominator and go from there. I think most people would probably want to get rid of the denominator, so multiply everything by cosine x. So if we do that, we get cosine squared x plus sine squared x equals 2 cosine x. Now cosine squared plus sine squared is one of the trig identities. That's the Pythagorean identity where that equals 1. So this gives us 1 equals 2 cosine x. So now I can solve for the cosine of x. I'm going to divide both sides by 2. I get 1/2 equals cosine of x. And now I'm just looking where on my unit circle is cosine, which is the x value, equal to 1/2. And because we don't have to worry about the period, because we're in 0 to 2 pi, there's only 2 spots, pi over 3 and 5 pi over 3. So x equals pi over 3, 5 pi over 3. We don't have to worry about any of that n business. Okay, now this is my last example here. We have 2 secant squared x plus tangent squared x minus 3 equals 0. Again, we're given the interval 0 to 2 pi, so we don't have to worry about the n stuff. So now we just have to figure out, well, how do we want to solve this? So there are sort of multiple ways to do this. So let's just see what happens. So your thought might be, okay, let's secant is 1 over cosine, and tangent is sine over cosine. So let's just convert both of those and see where this takes us. So 2 secant squared of x. So secant squared, then that would be 1 over cosine squared. Because if I squared both sides, that'd be 1 squared over cosine squared. So I could write this as 2 over cosine squared x plus, if I square tangent, I'm squaring the sine and the cosine. So that's going to be plus sine squared x cosine squared x minus 3 equals 0. So let's say you want to get rid of the cosine squared x, the denominator, and so you can just multiply everything by cosine squared x. This would give us 2 plus sine squared x minus 3 cosine squared x equals 0. Okay, well, sine squared plus cosine squared is identity, but we don't have any identities from sine squared minus 3 cosine squared. So let's take a look at our identities, see if there's anything that we can potentially use. We can't use the Pythagorean identity there. 1 plus tangent squared, 1 plus cotangent. What we could do is maybe solve the Pythagorean identity and say sine squared is 1 minus cosine squared. So we could try to see where that takes us. If this would let me go to other slides, there we go. So let's try that. Let's just convert sine. So that would be 2 plus, and then sine is 1 minus cosine squared x minus 3 cosine squared x equals 0. Okay, we got 2 plus 1, so that's 3. And then that'd be minus 4 cosine squared x. All right, 3, oops, I forgot, equals 0. Let's add the 4 cosine squared x to both sides. 3 equals 4 cosine squared x. Divide both sides by 4, we get 3/4 equal cosine squared x. Let's take the square root of both sides. Square root of 3 over 2, we'd get a plus or minus equals cosine x. Okay, that's something we can do. So let's take a look at our unit circle. So our unit circle, we're looking for all the x values where we have square root of 3 over 2 in both positive version and negative version. So I have pi over 6. I have 5 pi over 6. Let's see, we've got 7 pi over 6 and 11 pi over 6. And all we want are the ones that are in our interval, so we have 4 answers here. So x is equal to pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So now we just found we got 4 answers. Now, when I went over to our identities, notice that we did have, whoops, wrong one. Let's go back a slide, if it would let me. There. We also have identities with tangent squared, which is secant squared. So if we wanted to, we can convert the secant squared to 1 plus tangent squared. So let's do that. Let's see if we get the same answers. My thing does not want to cooperate. Okay. So I'm going to do this in a different color. I should have done 2 slides here. Let's say instead of doing what we did, where we converted everything to sine and cosine and went from there, we use the identity that secant squared equals 1 plus tangent squared. So this is going to be in blue. So that means instead of 2 secant squared, we have 2 times 1 plus tangent squared of x plus tangent squared x minus 3 equals 0. So I'm sort of squeezing this in here. Should have made 2 slides. Okay, so that will give us 2. I'm going to try to distribute and simplify at the same time just because I'm limited on space. So when I multiply, I'd have 2 and then minus 3, so that's a 1. And then we get 2 tangent squared x plus tangent squared x is 3 tangent squared x equals 0. So now we can solve. Let's say I subtract 1 from both sides. I get tangent squared x equals negative 1. Oh, wait a minute. 2 minus 3 is a negative 1, so I should add 1 to both sides. So that gives me a positive 1. And I've lost my 3 there. Divide both sides by 3, so we get tangent squared x equals 1/3. And then we take the square root of both sides, which would give us tangent of x equals plus or minus. Square root of 1 is 1, so 1 over the square root of 3, which when we rationalize is plus or minus the square root of 3 over 3. And now we would need to figure out which angle matches with that. So I'm going to use my graphing calculator here because my unit circle doesn't have the tangent values there, and I don't want to have to draw a triangle to try to figure out what it is. So I'm going to just do the inverse tangent of, let's just start with the positive 1 square root of 3 over 3. It gives me pi over 6. So I see we get x equals pi over 6. And then because there's the negative version, you can find the negative version, and Then you can use your period, which is pi, to get to each answer. So we get to the same answer. I think this method was maybe about the same number of steps. You didn't have to deal with fractions, but for me, I don't have the tangents memorized on what angle goes with square root of 3 over 3 and all that, so I prefer to always put them in terms of cosine and sine if possible, because then I can get it off of my unit circle. But you get the same answer either way. It's just a matter of trying to figure out which makes sense to you and looks kind of makes sense with the way that you think. So that is it. That is giving you a good overview of how to solve these things. If you have any questions, you can email me or give me a call, and you should be good to go on doing the assignments for this week. All right, hopefully I'll see you guys at my next live session.